essentially the lecture today, as I would record it, I'll stop at the end, for some questions, discussion for 10 minutes, and then I'll pick back up recording lecture 4. Then we'll probably take a short break and do lecture 5. So don't feel compelled to stay, but if you want to stay, you're welcome to. It'll be posted online essentially early afternoon. And then also, I won't be here for my office hours today because I'm recording the lectures Wednesday and Monday. Yingxie should have some extra office hours to make up for that this week here. And then you can send me email. I don't know my email situation this week, so don't send me something expecting like a reply in the next 10 minutes because I'll be 9 time zones away and, I don't know. Hopefully I'll have internet. You never know. All right. Fick, guys, are we ready?
You're on.
I'm on. All right. Well, so let's go ahead and get started here. So this is lecture number 3, the Wireless Communications Lab. I'm Robert Heath, University of Texas at Austin. So first, I'll explain what we're going to do today. So the first thing that we're going to do is we're going to review the components of a digital communication system. In particular, we're going to go through the last 2 pieces I didn't get to last Wednesday, which is modulation, demodulation, and the channel. Then the second thing that we're going to do, and we're going to spend hopefully the majority of class on this, unless I just keep talking about the communication system, which is a quick and dirty review of stochastic processes. Now, the prerequisites for this course all require 351K, which is our undergraduate probability and stochastic processes course. Now, I know that many of you don't actually see stochastic processes in that class, so I will review the basic concepts of what we need, which is essentially wide-sense stationarity. So I'll talk about that, and and I have to admit that this lecture in particular is going to have just a lot of definitions and things, and I have put a lot of work into providing examples in the textbook, but I confess I won't go through, I don't think, any examples today. So it's going to be a bit dry, but it's very important because we are going to need these concepts throughout the rest of the class. And if you didn't like probability, I apologize now, but you're not going to enjoy this, and unfortunately, it's part of the whole of digital communication. I mean, randomness and uncertainty is critical. So that's what we're going to do the rest of today, at least in lecture 3. Okay, so now let's get started with the components of a digital communication system. So let's start off here with, sorry, I'm trying to get the timing set up here. Time, all right. So this is going to be lecture number 3. Can't see that, that's there. So here's the block diagram that we spent a lot of time talking about in lecture number 2. And so this is a typical digital communication system. It's an abstraction that forms the basis of a lot of different aspects of communication. So we talked last time about the source and the sink, the source being the origin of binary information or bits, and the sink being its destination. And then we talked some about encryption and decryption, used to make that transmission secure, whatever that means these days. Source and coding and decoding. This is where we're going to compress the source, to reduce the amount of bits that we actually need to send. Often this is done at the application, though it depends on exactly on the system. In a cellular phone, the vocoding is done, sort of as part of the communication process, whereas if, you're exchanging video with someone, the video is already compressed at the source already. Channel coding is about adding extra redundancy so that we can correct for errors. And those errors are due to things like noise in particular, and that we'll talk about some today. So these are the ones that we went through in detail. And what we're going to do today is we're going to talk about the modulation and demodulation pieces, and then this whole piece right here, which is the channel. And so with that, let me find my stack of notes here, since I'm multiplexing like 3 lectures at once. I have like a phone book of notes up here. Okay. All right. Okay, almost ready here. Let's see. Okay, so this is a continuation of this little box here, components of a digital communication system. So this is supposed to continue the set of bullets that we had last time here. I know it may seem strange that I'm using effectively PowerPoint notation and I'm writing it out, but you know, that's just the way I think about it from an outline perspective here. And this is my favorite top bullet, is the filled in box here. So the, oh shoot, that is my phone. Okay, so first of all, let's talk about the modulation piece, and then I'll mention more briefly the demodulation. But essentially, modulation is about taking our bit sequence and converting it somehow into a waveform. Now, modulation, you know, also from a signal processing perspective means other things too. It could be multiplying two signals together. We also call that modulation. But here, digital communication, we think of modulation as this process here. So there's a whole bunch of different kinds of modulation. And they're classified in different ways. For example, linear or nonlinear, or memoryless or with memory. And many of these distinctions you'll find if you take, you know, a class in digital communication like 362K. Now, in our case, you know, we want to focus on a specific type of digital modulation, not look at every possible modulation that you might see. And so for that purpose, what we're going to do is we're going to focus on what I call complex pulse amplitude modulation. And this goes by different names in the literature. You know, usually it's some variation of pulse amplitude modulation, but I'm calling it complex pulse amplitude modulation to emphasize that we're going to be using complex signals in one step of the process here. So the way that we can write this here, let's see. Yeah, this is a pain, like scrolling this up here. All right. So the way that we can write this in block diagram form essentially is as follows here. So we have what I'm calling rather abstractly just now bits. It's a sequence of bits here. And I'm going to break the modulation into two pieces. The first one is going to be the symbol mapping operation, which I'll call symbol map here. And then the output of this is going to go into a block that I call pulse shape. And the output of this is going to be a continuous time signal that I'll call x of t here. So first off, let's explain what each of these different pieces does here. So first is the symbol mapping operation. So for the symbol map, into this block here, I'm going to put as an input this C, this a calligraphic C that's like a set of, in this case, symbols. So I might write this as C1, C2, ... Cm. And so this calligraphic C, the set, we're going to call a constellation. There's m total points in the constellation. And then each C of k, which is an element of C, is a symbol. And so this is an element of the set C, which is a constellation. And in this class here, primarily we're going to deal with symbols that are either real or complex, typically complex. Now, at the end of the class, like at the end meaning like lecture 23, when we start talking about MIMO communication systems, we'll actually generalize this to make the symbols vectors. And naturally, you could also make them matrices and higher dimensional objects, but that's the extent that we're going to explore them in class here. Now, what the symbol mapping operation does is, first of all, we need to illustrate this idea of constellation. So let me show it down here. So first of all, let's put the constellation over here. So we'll talk about different types of constellations in a couple lectures when we start going through some of the other details of digital communication. But for now, I'll just give you one example here, which is called 4 phase shift keying. And the way we illustrate the constellation is, if it's complex, is we write this real and imaginary set of points here, and then we typically label the points looking something like this here, like with little circles. Of course, you could use diamond or something else here. And so then I might call this, C1, C2, C3, C4. Now, the thing is that we are mapping binary information onto one of these points here. We have 4 points, so we can represent 2 bits of information. So we also will label these points with a pair of binary numbers. And this is known as bit labeling. And again, we'll go through this in more detail in a couple more lectures. Now, with the way that I've set this up here, my constellation, so supposing that this is a 1 here, and this is a J, my constellation would be 1, J, minus 1, actually, let me think here, 1, 2, sorry, it's going to be, if I go in binary order, it's 0, 1, 2, 3. So it's going to be J, comma, minus 1. And this is sorted in this binary order. Could someone close the door in the back at some point? Thank you. And so this is a trick here. I mean, the constellations themselves, you don't necessarily have to order the set like this, but I find this useful because if you're doing the mapping in your code, then this is like 0, 1, 2, and 3. And otherwise, you have to do some extra permutation here. So this is just an example of a constellation. So we're going to take bits that come in and assign them one of these 4 labels. And then just to illustrate that, let me put here an example mapping table, which is somehow what I meant to put over there here. But so this would be bit mapping table. And so supposing that so this is 0, 0, 0, 1, 1, 0, 1, 1, 1, J, minus 1. And this corresponds to C1, C2, C4, C3. And then just as an example, shoot, I said I wouldn't have any examples, but I'm sorry about this here. So suppose we had this sequence coming in like this here. So we've got 1, 2, 3, 4, 5, 6, 7, 8 bits coming in. So we would partition these into pairs of 2. And then we would apply this mapping table here to generate the output 1. So 0, 1 would be J, 1, 1 would be minus 1, 1, 1 would be minus 1 here. And so this is the output And then other things to note is that there's 2 bits here per symbol. So this is essentially what the symbol mapping operation is doing. It's taking the sequence of bits and generating a sequence of symbols at the output. Now, the next step here is the pulse shaping operation. So, we might write this sequence of symbols here as a discrete time signal S of n, and we put that into some block that generates out a continuous time signal. So there's something magical happening here. We're going somehow from sequence to continuous time, and that's where the action is here. So let's write now, let's see. Just imagining here, I'm going to go through my paper quickly. All right, let me try to write it over here. So let's write this block here. S of n goes into the pulse shape, and then spits out an x of t. So for complex pulse amplitude modulation, this functional form is very specific, and it looks like it's an infinite sum, say from minus infinity to infinity, of S of n g tx of t minus n capital T. So we've got a few things to look at here in the equation. This is our sequence of symbols, real or complex numbers in this case. This G is our transmit pulse shaping filter. And that capital T there is called the symbol period. I have to be careful. I think later in the course I'll probably put a TS here. Okay, and so this is the way that we're going to take symbols and map them onto the continuous waveform. Now, as an example, we could look at, let's say, all right, I'll put the example on a different page here. So suppose that we had a pulse shape that, for sake of argument here, looked like, this is going to be simple one here. Suppose this is t, this is 2t, this is time, this is the function gtx of t. Pulse shape is just a function. So in this case, the function looks kind of like a square wave, and then it's got a little triangle here. Then it goes to 0. This is not any kind of a function we would use in wireless. It's just for example purposes here. And then, let's look at, okay, so suppose our signal x of t, we have this infinite sum. So let's say we've got, so s of minus 1 is going to be tagged with g of t. So if we go back to this formula here, so for minus 1, we're going to get gtx of t minus ts, which is going to be plus t. So I'm going to put g of t plus t plus s of 0. This will be g of t, and then s1 will be g of tx of t minus capital T, and this whole process here continues. So you can transmit a whole infinite sequence of possible symbols here. And then just to illustrate how that would look would be, you would sum up here, when you take this g of t here plus capital T, you're going to shift it back, right? So this is going to be, and we're going to multiply it by s of minus 1, which I haven't told you about here. So this would be g of t plus t, and then this is going to get multiplied by just a scalar s of minus 1. And then you're going to add on top of that a pulse g of t that will be multiplied by s of 0. And then you're going to add on top of that a pulse it looks like this here. And so this is going to be g of t minus capital T, and this will be multiplying s of 1, et cetera here. And so then when you add all of these up, you get some complicated looking waveform here. But essentially that's the idea. So with complex pulse amplitude modulation, a complex number rides on top of a pulse. And then that pulse over time gets shifted and shifted and shifted. And in wireless systems, we'll find that these sharp edges here, they create signals that don't have very good spectral properties. And so we'll typically use something much smoother. And the smoother thing is much harder to illustrate. But anyways, that's the idea here of the modulation that we're going to consider in class. So any questions about this? Just the symbol mapping, modulation, symbols. No questions. Okay. So now I'll talk a little bit about demodulation, and then we'll wrap this up and get into the stochastic processes review. Actually, we'll talk about the channel, then we get into the stochastic processes review. So the demodulation block is tasked with kind of the reverse of this here. It's going to take, at its input, a noisy waveform, and it's going to produce at its output a reasonable guess of the sequence of bits that was sent. And I put this little hat we use in signal processing to denote like an estimate, something that is uncertain, the result of making a decision. Now the demodulation piece, it turns out, is a bit harder to draw in a generic fashion because there's a whole lot of different ways that this demodulation can happen, but usually, like the way that we're going to consider it in class, there's going to be essentially two pieces. There's going to be a filtering operation, and then there's going to be a symbol detection operation. And I'll skip the filtering for now because that will fall out of some of the work that we do in a few lectures from now. But the symbol detection I'll mention. Essentially, the idea is that taking our same example constellation as before, the symbol detection piece will get an observation and then a mathematical algorithm will be employed to try to see, okay, should we decide that this observation was, in this case, 1, j, minus 1, minus j, or the equivalent bits. So was this a 1? Was this a j? Was it minus j? Was it minus 1? And solving that is the detection problem here. And so what we'll see is that we need to build up a mathematical model for why what we sent didn't land exactly where we thought it would due to noise, interference, impairments in the channel. So we have to build a mathematical model for that, and then we can derive what's called a detection rule. So we'll derive in a formal way an algorithm that will tell us, how to decide if this point should be one of these other points. And so that's part of detection theory, and that's a big component of statistical signal processing. So that's what the demodulation is doing. And then there's a whole lot of variations of this, and there's soft and hard information, and that can be used as well. Okay, so that's the demodulation piece. Now, the last block that I want to talk about is the collection here of analog processing, propagation medium, and more analog processing, which we lump together into the channel. And so in the channel is our model that includes analog and propagation effects. And so we're going to see things like that we're going to have, let me see, additive noise. So for example, additive noise, and this will be where we observe a signal y of t that consists of, let's say, for example, a signal x of t that we sent plus something else here. So this you could say is, this is our signal that we constructed, and this is additive noise. We'll talk a little bit about noise later today in the stochastic processes example. But this is an example of a kind of a channel. So the channel is a model for our received signal. And so we say that, okay, all the analog impairments and everything, it contributes to this unknown quantity here that we're going to call noise. And then we're going to develop a mathematical model for noise and use that to derive, detection boundaries. So that's like something that comes from the analog piece. And then from the propagation piece, what we're going to see is that our signal is going to be launched into the environment. It's going to reflect and diffract and go through different objects here. And so when you have, sorry, this is actually is an antenna array. I'm just so used to drawing things with multiple antennas. Anyways, you get the idea. It's one antenna, let's say. So when you send a signal into the environment, there's no obstruction. It propagates along and lands at the receiver. But in reality, there's stuff all over the place, and so you get things like reflections. You're going to have diffraction around buildings, and all kinds of smearing will happen here. And the net of it is that you'll receive, let's say, your signal x of t delayed by some tau. That's the propagation delay. But then you'll also receive another version of that signal. That'll be attenuated. And then you'll receive another version of that signal that's attenuated more, delayed even further, plus another version of that signal that's delayed even more. And so you get attenuation, delay here. And so these are other impairments that we'll have to deal with as well. And we'll model this effect here as a linear time invariant system. And so then we'll do that, let's see, in lecture 4 or 5. It's either 5 or 6, actually 6, because I didn't have that one for today. So lecture 6, we'll develop a model for this in using some signal processing techniques. So that's the other piece of the digital communication system, is the channel. And the modulation, demodulation, and channel, we're going to deal with a lot in the course. So I'm not going through it in as much detail here. So that's, again, the block diagram. So any questions about any other piece here on this communication system here? Yes.
The analog processing exactly denote, like in channel?
The analog, yeah, that's a good question, and I did not explain it enough. But there's a ton of different things that are happening in the analog. Essentially, there might be mixing operations where you take your signal and you multiply it by a cosine of some frequency. There's going to be amplifiers. There's just tons of stuff. It's basically anything that happens in the analog domain. And what we'll find is that the modulator, at some point, will have a digital to analog converter in it. And that after that point, there's a whole bunch of stuff in analog. And so there's all these operations here. And then if you study RF electronics, you find that each of these operations introduces noise. And they also introduce nonlinearities, too. So all that could also be included in here. Now, usually, we design the system such that it's as linear as possible, because dealing with nonlinearities is very hard. But in theory, all of that can be lumped into the channel. So you have phase noise, you can put it in there. Anything that's kind of non-ideal goes in that channel. And there's work on coming up with better mathematical models for the channel. Because if you have a better understanding of exactly how your signal is distorted, you can make a better decision about what was sent. And so there's sort of this interesting set of research which is like on better characterizing analog and using that information to do better detection. So. Yes, question?
So what does the complex part of the signal that you're transmitting physically represent?
Yeah, that's a good question. We will talk about that in, it's either lecture 4 or 5. So we will get to that later today. Essentially, we cannot transmit a complex signal. That doesn't make sense. But it turns out that the real and imaginary pieces will each ride their own orthogonal signal. And in particular, the real part will ride on a cosine, and the imaginary part will ride on a sine. And so we use complex as just a way of dealing with 2 dimensions. So that's like the short answer. And we'll see exactly that. The end of lecture 5, we'll talk about exactly what that means and how to create it. And that's an important point because of that fact that we can send both sinusoids, like real cosines and sines, and this all comes from basically just Maxwell's equations, we are going to deal a lot with complex signals. So maybe in probability you might have talked a lot about real signals and not complex, but pretty much everything we have to do is going to be complex. All right, any other questions? Okay, so let's continue here with short break. Intermission, I think, is what this is called. Haven't been to a movie in many years. Actually, in the U.S., movies don't have intermissions anymore because they're not that long. Okay, so we had this discussion last week on this concept called the watch. And I thought it was very well timed because it was either that day or the day after that, I started seeing this advertised here. So this was like a big deal. There's been rumors of this, and there's various companies that have been putting something together, but the Samsung one is just getting, I think, the most press out of all of them here. And so this is and I'm not trying to advertise for Samsung. I want to talk about the concept here. The Samsung, if you're listening, give me a call. We're flexible. So these are smartwatches. And the idea of this particular watch is it's going to display information that appears otherwise on your Android phone. So it's not a phone in itself. And it's just a way of viewing information on your phone without taking your phone out of your pocket or handbag or backpack. And so their claim is that it's inconvenient to take it out of the pocket. And I mean, I can kind of believe that because I have this like rubbery case on my phone because most at least professors, I drop this 5 times a day, and so I have to have it on here. And yeah, it adds friction, so it makes it hard to take it out. And if you have those even bigger phones, maybe you don't even want to pull it out. So that's the idea. Sort of interesting. It's going to come in different colors and different shapes. This is not curved, by the way. This is flat. So the real innovations are probably going to happen when this becomes curved. But anyways, this is also pretty big. It's bigger than my watch now. And so you can see, for example, look, you can get both the time and the weather at the same time. I suppose that's cool. It's got a little microphone, and I don't know if this is a microphone or camera. Okay, that's a camera. What on earth are we? So this is like like you take a photo like this. Cool. Good buddies in the government will love that. Yay. Yeah, so there's a whole handful of them here. Anyway, so I just thought this was interesting that maybe the watch is going to make a comeback in some very different form than we're kind of imagining now. Does anyone have any comments on this? Would anyone use this? Yeah.
Have you heard the recent news story about there was a morning show anchor that got a call on one of those smartwatches, I guess, and accidentally exposed her number on national TV.
Cool. Should we call it? It's
she already changed her number since that incident. But
yeah, that was probably is that with the Pebble watch? I know that's another one.
I don't remember exactly, but yeah, it was very recently.
Yeah, and there's different companies that have variations of this. Yeah, I think that is a concern. Yeah.
I think whenever they integrate like solar power with it and the curve and the fact that if you don't have to carry your phone with you to integrate with that, then
Yeah.
that will start being a better hit.
But it has to be then its own phone, essentially.
Right.
Because, I mean, if you leave your phone at home and take your watch, then it's
Yeah.
pretty much its own device.
Right.
Yeah. There was another comment? Yes.
How robust would the watch have to be if, like, you're worried about your phone breaking? How, like, then would it become like worrying about your watch breaking?
Yeah, that's a good question. I mean, I think depending on the audience have to be reasonably careful. But, you know, I mean, people wear expensive watches all the time, and watches are, you know, they have little sapphire and stuff on it, but they are prone to getting dented. And but yeah, I think it's a concern. But that'll just create a whole secondary market of people making this, you know, rubber case that goes around the watch, and creating a screen cover, and you know, it'll just be. And that you know, the watch will be $100, the cover will be $40, and the LCD display will be another $10. Yeah, I don't know. So, yeah, it's an issue. I would probably scratch the crap out of it. I also wonder how waterproof it is too. If it's waterproof at all. I mean, it has to be reasonably water resistant, I think. That's a good question here. I just flooded like a few months ago my favorite watch, and I'm still like reeling from that. Fortunately, if you have a stainless steel watch and you get water in it, this is an actual watch that has a mechanism inside, and I got salt water in it, and took it to the watch place, and they just kind of shook their head like, well, got to send it back. That's a big problem. Anyway, so yeah, I'm sensitive to that. But this could be awesome for scuba diving if it could go to 60 meters or something. It'd be really cool. I have a dive watch that's sort of a little bit bigger than this, but has kind of a similar form factor, and that's really useful.
You gotta bring your waterproof cell phone as well.
Yep. Yeah, and they have some good packages for that. I mean, you can now, actually there's a dive watch that you can put your phone in, kind of like these camera cases that's good for 120 or 200 feet. And so essentially your dive watch becomes like your phone in a massive plastic case on this, and then the case has some sensors integrated for pressure. So you can actually see the depth, and you can even get a wireless interface to your tank and display it all there. So that's pretty cool. Yeah. I did a lot of scuba diving over the summer, so I'm like psyched about it now. I'll say I did not get the wireless interface because I think wireless is too unreliable, especially underwater. So I'm waiting for that to get a little bit better. Anyways, I don't know. I just thought this was cool. Any other comments on this?
So does this
Yes.
connect with Bluetooth or something else?
That's a good question.
It does.
Oh. I want to say it's either Bluetooth or Wi-Fi Direct.
It connects to Bluetooth.
Bluetooth? Okay. Yeah, so your phone has to be reasonably close then. Yeah.
It's also really expensive.
How much is it?
300.
300. Oh, that's a good deal. That's like the price of the phone, subsidized phone, and then yeah. But I mean, man, it makes sense. If everyone has a phone, what are your options here? Sell everyone another phone, sell them more phones, make them break or not last long, or upgrade them, or sell them stuff to go onto their phone. So I don't know. I like the spirit of this here, not as a consumer, but, as an entrepreneur, I think it's a cool idea. Okay, so with that, now we're going to make a very abrupt transition into some super related concept in the class called stochastic processes. And again, this is perhaps the most important background review lecture that we will have is this on stochastic processes. And I really encourage you to read this part of the book carefully, to review your previous textbooks as needed, because I've just seen so many students get hung up on these concepts, and then it just interferes with your ability to succeed in the course, which I don't want. So the main things is, first I want you to be able to explain the application of random processes in wireless communications. So just essentially tell me why we're doing it. That's important. You should always be able to do that, but in this particular case I want you to be able to do that. The second is, in particular, we're going to calculate the mean, covariance, and correlation of a stochastic process. So I want you to be able to do that, and I want you to be able to do it in two ways. One, using expectation, and second, using ergodicity. or time averaging here. And so expectation is the technique that we will use like on homeworks and you use on paper to derive intuition. And ergodicity and time averaging is what you would actually do in the lab to measure something. And so we need both of these because we need to talk about wireless theory, we need to talk about wireless, how it actually works in the lab. So that's where we're going here. So now, let me just organize my notes over here. Okay. All right. Now, I'm going to peek right here. 6. Okay. All right. Got to find a way of keeping track of these numbers better up here. If I had a smartphone or a smartwatch or something that would help, right? Okay. So stochastic processes. So first of all, I'm going to give you a kind of the loose definition. And I'm never going to give you, truly formal definitions of everything here, because that's in itself like several weeks of class. But loose definition of a stochastic process or a random process. And these are just used interchangeably. They don't mean anything different, at least to me, is that it's a probabilistic model for a random signal, sequence, or function. And so this is the main departure from conventional probability, where you focus on characterizing, let's say, a single random variable, the outcome of rolling a die. So here we're going to talk about a sequence. So if I roll a die many times and I get many observations and I convert that dice rolling into like a discrete time signal, and then we're going to characterize that. So that's essentially what a stochastic process is. And it could also be a function. It could be a random function or random sequence. So one thing that's important to note, is that when we talk about like a random signal, sequence, or function, what we want to do is we want to characterize an ensemble of such sequences / functions. And so, the typical picture here, you've got this probability space, you've got these outcomes, so outcomes of our probabilistic experiment will have the form of, functions or signals instead of numbers. And, that's the main technical difference. And it turns out that this is a very technical area that has deep mathematical foundations. So, for example, if you've taken real analysis, I forget the course number here at UT, but there's a whole bunch of different real analysis courses. The main one that our undergraduates take goes through a number of important concepts, but typically cuts off before you get into measure theory. And so really, to understand probability, you have to take more advanced courses where you talk about measure theory and understand integrals as on the big measures, and it's intimately tied together. Now, fortunately, for most practical settings, us engineers, we don't really need to know all of that. It's good to know that that exists, and if you want to do a PhD that's very mathematical, you might need some of those tools. But for the most part, we don't need those tools in real systems because things are typically well behaved. Mathematicians are really concerned with a lot of times what I think as an engineer we call a corner case, something that's just sort of bizarre and intriguing but doesn't happen in reality. Not to put off any mathematicians here, but that's just kind of the, it's just a difference in emphasis here. And that's important, but we don't need so much of that. So that's essentially the definition. So what I'm going to try to do is go through some of the key concepts here. Now, first of all, I promised we talk about why. So let's get through the why stochastic processes, and then we'll start off with probability and go through some other topics here. So as a signal processing engineer, I mean, I've used stochastic processes as as a model. It's a model for something in reality where we don't know for sure what's going on. So stochastic process in communication signal. Well, let's talk about transmitted information. So the transmitted signal, or let me just put information here. So we talked before that, if the receiver knows what the transmitter is sending, it's not being informed. So there has to be some notion of uncertainty there. Turns out that a good model for that uncertainty is to use a random process here. So transmitted information, for example, the bit sequence that we send, well modeled by a random process. Now, to avoid spelling out random process all the time or stochastic process, I'm just going to write RP. So the things that we're sending, we can model using concepts from random processes. Another one. We already talked about this, thermal noise. Thermal noise is the electrical noise that's caused by thermal activity, the random motions of electrons. And it turns out that the little random motions of electrons in all of our electrical devices, it creates small fluctuations in the signals that we send and receive. And those fluctuations are really small. But it turns out that the signals we're receiving are also really small. And so those little tiny fluctuations in a communication receiver have a huge impact. And this is caused by thermodynamics. I mean, there's no real good model for it, kind of deterministic model. And so we model it using a random process here. And so thermal noise, and let me just put here, one of the most important sources of error is well modeled by an RP. And then further, the propagation environment. Now, if you think about this from an electromagnetic perspective, we have a transmitter on this side and a receiver over here. We could model everything in here. All of us, we could model based on our material properties. We could do a ray tracing simulation and compute the field strength all over this room, right? It's deterministic. The thing is that whenever someone moves, shifts around, or we don't know exactly the material composition of everybody. I mean, I'd have to know what you ate for breakfast and all of that. It doesn't make any sense. That introduces uncertainty. And so we typically, from a signal processing perspective, we often model the channel, the realization at the receiver as kind of a deterministic quantity. But when we're talking about performance analysis, we model it using some sort of a stochastic process here. So the propagation channel is well modeled by random process, and I want to emphasize here, due to mobility and uncertainty. And so we might build a model for the transfer function between any 2 points in this room, and then make it a stochastic model, and then we might say, okay, how does my communication system work on average in this room? And so I would somehow average over all these different locations. So that's a way that we use random processes to model the channel in wireless. And that's something that we're going to do. That's kind of like lecture 19 or 20 where we do this. But this is going to be like lecture 6 or 7. And this will be similarly as well. So that's kind of the why piece, why we want to do this here. So basically information, noise, channel, and then our receive signal, because it goes through this potentially random signal, it gets augmented by random noise, is also random signal. So randomness essentially is coming everywhere here. And because we're not sending just one piece of information, we're sending a sequence, and we're creating a signal, and we're demodulating a signal and creating another sequence. We need both continuous and discrete random processes. So just a little bit of review. A lot of this review is just to introduce you to the notation that I plan to use. So from the perspective of, so first of all, I'm just going to talk about probability, not random processes yet. And so for a continuous valued, and then this RV is random variable. So I'm going to let f of x of t denote the probability distribution function. And then I'm going to use the capital F x, let's say of alpha here, as the cumulative distribution function. And so this is the cumulative. Okay, so some things about the notation. The random variable that we're talking about, I put it in the subscript here. This is x. The t here is not time, it's just a dummy variable. It's just a function. Cumulative distribution function, we call it that because it is accumulating. It's summing up from minus infinity to alpha of that probability distribution function, and this is an integral here. And so this is a function of, for example, alpha. This is a function of t. Now remember, there's nothing sacred here about the alpha. This could be g or gamma or just anything, right? It doesn't matter. It's just a dummy variable. This x, though, is important because it means that I'm talking about the cumulative distribution function for some random variable x. Now, this is continuous valued random variable. We also have the fortune to deal with discrete valued random variables. Not as much, but we do deal with them here. For example, binary information, 0 or 1, that's discrete valued. So discrete valued random variables have only finite set of outcomes. Let's say integer outcomes. I mean, because you could extend it to all of the integers here. So for example, let's let x, calligraphic x, denote the set of outcomes. And then we'll let m on this integer set 1 through the length of that x here index the values. Then px of m will denote the probability mass function. Of the mth outcome of random variable x. So the notation here, so I could say, you know, like if my possible outcomes were, let's say, 1, 2, and 2.5, effectively this, I'm just labeling 1, 2, and 2.5 using 1, 2, and 3. And then I'm saying that, you know, the probability of 1 is this, probability of 2 is this, probability of 2.5 is this. But I'm just using this discrete time sequence notation to index it. It just makes it a little bit easier with some of the calculations. Now that said, there's only a few cases where we use the discrete valued random variable, primarily for binary information and for symbols. Okay, so that's, yeah, and then let me talk about mean and variance here. So we need to operate on these random variables here. And so we use this notation and this is what, if you look in the text, is for the most part in the book, I have converted everything over. Not everywhere, but I've tried to catch all of them here. This is called a blackboard notation. So this is an E, which we're going to represent as expectation. And so this is an operator, and if I take the expectation of some random variable x here, what that means is that I'm going to integrate the possible values of x. And actually, I guess to make this a little bit less abusive a notation, let me make that t. So fx of t dt here, so if it's continuous valued. And you can define, a similar situation if it's discrete valued. It might look something like this here. You sum over all the m in those ordered set, except that you have now x of m, the actual values, times their probability. But this is the most important one to remember here. So this is like, expectation. So if I had expectation of x squared here, I would integrate with respect to t squared of x of t. So expectation essentially is just taking whatever is here and integrating it with respect to its probability distribution function. We can extend this to joint distributions as well. So this expectation is just a shorthand for this here. So that's the mean of a random variable, and then we'll also define various sundry moments here. Like we'll often use the notation sigma x squared as variance, and so that's the expectation of absolute value of x squared minus absolute expectation of x squared. And note here that I've been careful about the absolute values here. Yeah, so that's mean. So any question on that? Now one thing, this really bothers some of my colleagues here, but a lot of times when you take probability, you're very careful to distinguish between a random variable and its realization. And so often you use a capital letter as a random variable and a lowercase letter as its realization. It is historical in statistical signal processing that we just don't follow that convention and we just abuse the notation. And so we might write, I might have a signal x of n, and I might mean realization or random variable. You just got to keep track of it. So when we're talking about some of the DSP algorithms, it's going to be a realization because we're operating on actual numbers. And when we're doing some math, it's going to be a random variable. So you just have to be careful with it. Sorry about that, but that's just the way it's been for a long time. One of the reasons we do that is that we tend to make uppercase letters, bold letters mean other things. So we also have need for constants, vectors, matrices, and higher dimensional objects. So we just tend to have gone in that direction. And then if you have realizations and random variables of each of those, you need like a whole another set of notation to do all of that. It's a pain. So yeah, it doesn't work. All right, so now let's talk about random processes. So using this kind of same sort of notation here, so for a continuous time random process, so continuous time random process, x of t. T is the continuous time index, and this is t being in the set of real numbers here. I suppose it's possible to extend it to complex, but we don't do that. And then what you can think of is that x of t is a random variable at time t here. So what this means is that, x of t sub 1 is a random variable, x of t sub 2 is a random variable, etc. here. So we have, an infinite continuum of random variables to play with. One of the reasons it's so exciting. For a discrete time random process, x of n is the notation that we use. And I'm trying to use, the square brackets here to denote integer argument instead of continuous time here. N is an integer. And then we just treat x of n as a random variable. Now I know somehow this doesn't look like a square bracket, but it is. But yeah, unfortunately, throughout the whole semester here, the square bracket will eventually just look like a parenthesis. But you know what I mean, hopefully. Okay, so things that are important to note here about random processes. So for the most part, I'm going to focus on discrete time random processes because we actually don't really need continuous time that much in the class. So I want to focus on discrete time. And then there's different ways to characterize these random processes. So there's the characterization by essentially what you know about the process. Characterization. So first order is that you know the cumulative distribution function, or equivalently the probability distribution function for every n. So look what I've done here. I've written this fx as a function of n here. Not a mistake. So if you know the cumulative distribution function of x of n for every possible value of n, then you say you have a first order characterization of that random process. Now, if you know more than that, you might know fx at n1 and x at n2. And you know the joint distribution here. So if you know the distribution for every possible n1 and n2, including n1 equal to n2, then that's a second order characterization. The first order is a special case because essentially if n1 and n2 are the same, you get back to the first order. So, and this continues here. So there's what are called higher order distributions. Now, what we'll find is that, in fact, this kinds of information here, it's actually a lot. It's a lot to know the cumulative distribution function at all time. It's a lot to know this joint distribution function. So unless we make special assumptions, this is often too much. It's too much of a burden. So we will resort to a somewhat less cumbersome notion of what it means to know something here. So let me continue here to 10. Oh yeah, right. So before I get into that here, let me mention one thing, which is and I always forget to do this one, independent, so independent, identically distributed. This we abbreviate as something like this, IID. Sometimes it's abbreviated with all capitals here. This is actually the kind of random process that we're going to consider most in class. It's very easy to work with, fortunately, here. And for IID random process, then all the collections of random variables are independent. That's first. And second, they're all identically distributed. Distributed, yes. And so what that means is that your joint distribution function x of f of n1, x of n2, dot, 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 x of n k of alpha 1, alpha 2, dot, 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 alpha k is equal to f x alpha 1, f x alpha 2, dot, 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 f x alpha k. So essentially, this is the fact that we're multiplying all these together is the independent, and then the identically distributed is that this is f of x, is not x of n1, n2. So that's just a very common kind of random process that we'll consider. Any questions on that? All right. So now let's get into the moments of a stochastic process. So we're going to use the moments to build up a simpler characterization. And so for that, I have to define 3 quantities here. So I need the mean. And the mean I'm going to write as mx of n. And I'm just going to take the expectation with respect to x of n of my sequence x of n. And literally what that is I could integrate with respect to z, f, x of n of z dz, for example. So with a stochastic process, the moment, the first order moment, is a function of n here. That's like the main difference between this and a scalar, time. There's time in there. So if I have a sequence of random variables over time, every time I could compute the mean with it here, and that's just this expectation here. So that's the mean. We also need the correlation of a random process. The correlation is going to be written like this here. So the correlation is a function of only x. I'm writing rxx. Sometimes I write rx, but usually rxx. And then we have 2 indices here, n1 and n2. So what this is this is just the expectation between x of n1, x of n2, of the random variables x of n1, x of n2, and oops, look at that. That's an asterisk. That's a conjugate. Because we're dealing with complex random variables, we need to put a conjugate in place here. And there are other variations of correlation which don't have the conjugate, but things are still complex, and it turns out we don't need those. So this is the correlation function here. This is a 2-dimensional function because what we're trying to do is we're saying what's the average of the product of our signal at one point of time and another point in time. And so that's equivalent to the joint integration of the joint distribution here. And then finally, the covariance function. So the covariance function, we're going to write Cxx of n1, comma n2. And this is going to be the correlation function, Rxx of n1, comma n2, minus mx of n1, mx of n2, conjugate. This is the covariance function. And then note, importantly, that if 0 mean, then the covariance and the correlation are the same. And so most of the processes we consider in class are going to be 0 mean. Okay, and then let's see here. So that's the covariance. We call the variance, just based on substitution here, is going to be Cxx n comma n. That's the variance. And that's a function of n. So here we're saying, okay, if you go through and plug this in, you'll see that this was just a variance function as a function of n. There should be a 1 there. And then we say that a process is uncorrelated if Cxx of n1, comma n2 is equal to 0 for n1 not equal to n2. It's uncorrelated. And there's no equivalent, and this is a little strange because I'm defining it based on the covariance and not the correlation, but this is actually the correct terminology. Okay, so that is essentially the moments. Now, we're kind of looking at the time here. Okay, I'll do one more thing, and then we'll stop here. So the final thing that I want to do today is I want to define wide sense stationary. The wide sense stationary, which we'll abbreviate as WSS, is a characterization of a stochastic process or random process. Based on its moments. And so a wide sense stationary random process, x of n, satisfies two conditions here. One, the mean is a constant. What this means is that mx of n here is equal to mx here. So in going from here to here, so there's no time dependence. Now this is kind of nice, right? It means that, when you're looking at your random process, wherever you look, the average is the same. If you were to generate a whole family of random processes, get another realization, the average at a particular point in time would be the same. So that's what it means for the mean to be constant. The second one is also important here, and that is that the covariance is only a function of the difference. Equivalently, the correlation. Right? Because if this is a constant, then it just has a constant effect on all the covariance terms. So you can check the covariance or correlation. What this means is that I can write this function here, n1 comma n2. This is a two-dimensional sequence. And I can write this as a one-dimensional sequence with the argument n2 minus n1. So the intuition here is that the characteristics of the random process, if you're looking at time n1 and n2, it only matters how far apart n1 and n2 are. It doesn't matter where you look. So this is actually is important because, if you suppose you're doing an experiment, and we make a measurement now, and then we say, okay, are these random variables between 9 and 9:05 a.m. have exactly the same property, or I guess they have the same correlation as between 10 and 10:05 a.m. So it doesn't matter when you look. It only matters the time duration between the two. So that's essentially what this means here. So only time difference matters. And so when we say that a random process is wide sense stationary, it has a constant mean and a covariance that's only a function of the difference. So that's it. So if I give you a random process, and you'll see examples of this in the book, examples on this in the homework problems, you'll do homeworks on this. If I say, show that this random process is stationary, or otherwise, you'll have to compute its mean, compute its covariance, and see if both of these are true. And if one of these is not true, it is not wide sense stationary. I mean, that's essentially it. Now notice that, compared with what we were talking about, like, let's see, based on where did it go here? Based on this distribution functions, right? We don't say anything here about the distribution function. So nothing is said about fx of n, etc. here. Right? So all we're doing is saying that the mean and the covariance satisfy these properties. It could have different distribution, whatever. We don't specify that. Only care about these two quantities here. And then the last important point on this wide sense stationarity is that an IID random process is also wide sense stationary. So you need to remember that. So if I give you like an IID random process, you also know it's wide sense stationary. This is a very tricky way of proving a lot of things. And that, maybe we'll prove that on the homework. It's not too hard to do. Okay, so officially we out of time here for lecture 4. So let me summarize real quick where we have gotten here. If I can possibly find my lecture 4. Where's my... I can't find my lecture 4 sheet now. It's gone. Here we go. No, it's lecture 3. We're still on lecture 3. Shoot, 2 more to go. Lecture number 3. So we finalize our discussion of the components of digital communication system, talking about modulation, demodulation, and the channel. And these topics we're going to deal with a lot more in the rest of the course. So you'll see them again and again. And then we have talked about stochastic processes. You should explain why they're important, and you should be able to calculate the mean, covariance, and correlation of a stochastic process using expectation. We did not get to the last piece of ergodicity, but I'll cover that in the next lecture. And that's just the final piece there. And then in the next lecture, we're going to talk about Fourier transforms and sampling. All right, so that's it. I'll stop here for 5 or 10 minutes, take questions, and then for those of you that want to stay, I'll pick up with lecture number 4.
Can I see the last slide?
Which one?
Page.
This one?
The last one that you